E2E end-to-end network architecture extension for digital mobility services related KPI. 5G UK test network has integrated multi-vendor, multi-architectural and multi-thread designs in order to enhance current telecommunications services for a number of futuristic digital mobility use case demonstrations incorporating three different applications: APP1, APP2, and APP3. These applications have been defined according to the requirements set by the Digital Mobility UC Bristow as follows. APP1 provides the immersive uh, media and VR services to travelers arriving at MSHET. A synchronous 360-degree tour guide at specific geolocations is given to a group of users with 5G connectivity. In order to support user mobility, the facility at Bristol provides seamless connectivity to users when they are moving from one location to another, even during a boat trip. Edge synchronization and streaming server services need to follow user mobility and move to different edges accordingly. By doing so, a seamless visual tour guide is realized along the demonstration route in the city of Bristol. APP2 implements a remote training class taking place at the University of Bristol. Users with access to the 5G UK test network or the network at the University of Patros can stream the 360-degree VR camera feed in real time and at any location covered by the 5G UK test network or any of the two networks. These demonstrations uses service slice creation that spans across the corresponding edges connected to via infrastructure operating system. APP3 takes the advantages of low latency, high throughput 5G connectivity to provide real-time air services. An air journey takes place along the demonstration route, footpath and river, and includes a visit to SS Great Britain location before ending at Millennium Square, M Square. Network services such as synchronization, spatial data renderer, visualizer, journey planner, and video streaming services are deployed and run at edge and backend servers. Collection of users information including GPS locations data is required to predict user mobility and reduce the latency between the handover of edge services. Furthermore, the developed Android application provides passengers with location-specific guidance and multimodal transport journey planning beyond the starting location using AI techniques. Back-end GPU clusters deploying high-end GPUs provide the required air and AI processing at each of the edges. Figure 1.23, 2.13 provides the design of the end-to-end network architecture to support the demonstration of the digital mobility to use case within the 5G UK. This 5G UK test network architecture. An integrated instance of Zeta Automate networks is running at each stationary network edge and configures network slice on the required transport network switches. 5G BIOS instructs Zeta Automate to create, modify, delete network slices within the assigned edge nodes. Whereas the inter-edge connectivity manager within 5G BIOS responsible for the inter-edge slice management. End-to-end network architecture for demonstration digital mobility. This color L3 control panel, this color yeah, L2 data plane, L3 data plane, 5G net signal and connection this color. Okay. Then this is 5G VIOS. This one connect actually area. This is nomadic mode. This is MSHED. This is WTC. Here, this is a smart internet lab. This is journey box. Okay. This 5G VIOS connected to in nomadic node. 5G connected to MSHED and connected to WTC and smart internet lab. I have to tell, we have to discuss before that. Nomadic node contain edge proxy, uh, edge arc OSM, VIM OpenStack, SDN continued, I2CAT SM, VNF, OFSW, GNP, 5G core. Here in MSHED, Edge proxy, Edge arc OSM, VIM, OpenStack, SDN, VNF, OF switch GNP. And then in WTC, edge proxy, all are having edge proxy, all are having edge orchestra, OSM, and then all are having VIM OpenStack, SDN continued, VNF, OF switch. And then this one also in smart internet lab also having proxy cluster of switch, 5G core, edge proxy, edge orchestra, OSM, VIM, OpenStack, SDN continued, VNF, OF switching. Here UE, this UE connected to GNP connectivity here, journey path. Okay. So 5G VIOS connected to already we have seen. Then this one here in nomadic node connected to 5G, yes, and this off switch connected to this router like this. Here off switch connected to from MSHED cluster. From this off switch connected to cluster off switch. This nomadic node only connected to this router. And then this MSHED connected to 5G VS, and then in this it is having GNP. GNP connected to another GNP. Then GNP totally parallelly connected and then connected to 5G core. Here also GNP, that off switch connected to 5G core, 5G core connected to GNP, GNP connected to tower. So here in this smart internet lab having proxy cluster switch, proxy cluster switch, proxy connected to 5G OS, cluster connected to yeah, MSHED of switch and cluster of switch to off switch in WTC. Here then 5G core connected to this router connected to proxy clusters of this switch 5G core and directly connected to off switch of the nomadic node. So then this edge proxy connected to yes, yeah, 5G 5G VIOS. So now we can understand this color Okay, this color, this color L3 control pad, this one, this one, this one, then here, then here. Okay. Okay, L2 data plane. L2 data plane. Where is this color? No, this color. Okay. Then L3 data plane. This one. 5G net signaling connection. This one. Furthermore, 5G NR and Wi-Fi solutions are integrated in the 5G UK test network to support the required mobility services at the nomadic edge while also improving the 5G coverage of the area surrounding SS Great Britain at the locations where the 5G UK coverage is not sufficient. In addition, a slice manager component is responsible for network slicing at the nomadic edge. Compute resources are available at M Square, M Shed, and the Smart Internet Lab network edges, all of them being capable of providing the required MEC services to the mobility applications. Additional compute resources are also available at the nomadic edge in order to reduce the edge services provisioning time and the service mobility latency. MEC capability must be deployed closer to the end user, that is at the network edges. M shed, M square, SS Great Britain, all are at the network edges. Despite the relatively weaker backhaul performance at the SS Great Britain in terms of latency and throughput, local MEC services ensure seamless mobility within the record latency throughput KPIs. Architecture of for professional content production. The aim is to develop, integrate, validate, and demonstrate specific 5G components in E2 E5G infrastructure consisting of core network, radio access network, RAN, 5GC, and then and end devices for professional audio visual AV media content protection. It is shown in the 2.414 2.14 figure. Three specific use cases you see are addressed for its deployment, integration, and evaluation. Live audio production, multiple cameras, wireless studio, and live immersive media production. The live audio production use case, UC1 implements a full integration of audio capture devices, 5G RAN, and the production site. For the multiple camera wireless studio uses set of wireless cameras contribute AV content via 5G to a remote on site production room. Finally, the third use case delivers a live immersive media UC3 through a set of cameras wirelessly connected via 5G to the production room from where the content will be delivered on site via millimeter waves, wave or remotely. So, yes, 5G key enablers for professional AV content production. Yes, open and virtualized RAD, SDR, Red Cap UE prototype, URLLC air interface, dynamic spectrum access, design of 5G components for professional content protection. Then second one, this is for live audio production. This is for multiple camera wireless studio, non-public scheme, timing and synchronization, networking slicing, media orchestration, gateway, development of state-of-the-art 5G prototypes, integration into end-to-end 5G infrastructures, validation in the context of real production use cases.